had questions on was, oh, I didn't include the thing up top. Which one was this? This is B2. So B2, right, is particle in a box problem, the one where we're now extending it out to the 2D particle in a box. So a 2D particle in a box, right, we have the equation right there. All it is, right, a 2D, 3D is you just taking the equation that you have for the 1D particle in a box and you apply it to the x direction, and then you take the, that same equation, you apply it to the y direction, and you just multiply the two of them together, right? And that's how we get the wave function for the 2D particle in a box, right, in the x and the y direction. So, the first part of it is just the 1D, but the only thing different is that it's strictly for the x component, right? The second one is, the second half of it is just then strictly for the y component. And so, you multiply all that together, right? You do all of the math. That's how you get the energy equation that we have up here. And then if you make your life a lot simpler and you say, well, this box is actually a square, which means that the x direction and the y direction, right, those are going to be equal in those cases. You can simplify the equation down even further, because then L, right, is going to be the same for both of them, right? And you can pull that out of the equations and stuff. So when approaching, a 2D particle in a box, right, you can just simply draw, a box. And so all it is, when trying to figure out what does that particle in a box look like in these cases, is you can draw what the two different n levels, should be in those cases, right? So for, the first question here is, determining the probability of finding an electron in those following regions. So you can do it mathematically, right? So if you know how to do calculus, and you can integrate the wave function, and then you can, set the limits as, the different distances and stuff like that. You don't have to do any of that, right? Because you can pictorially actually figure it out, right? Because you can just look at how many quadrants and how many different things get spliced up. The only time you couldn't do that, right, is if we were giving you really weird regions of the box to look at, right? But it's you guys are at early enough of a stage that this is already confusing enough that we're not going to go that extreme, right? We're going to be using very discrete, very reasonable boundary conditions, because you would have to do the calculus, right? And there's no calculus for this class, right? That's not a requirement for the class. So, if you don't know how to integrate, from L, over 8 to, 3L over 16, right? Like that isn't gonna, you can't do that without doing calculus, but you can draw out what it looks like, and then it works. And so the way that you can approach this, for these right here, right, we know that, this is 0 to Lx, and this is 0 to Ly. We know that Lx and Ly are equivalent, right? Because I said that, right there, where I just simply said, Lx, the distance, right, they're equal as a part of the problem. And so we're looking at the n equals 2 system, right? And I realized that I forgot to put in that, both nx and ny are equal to 2. So that's on me, and I hope that's not the point of confusion that people are having. But right, so if n, if for the wave function in the x direction, right, if that's n equals 2, then that means that wave function, right, has a single node at the L equals 1/2 point, right? And then same thing here for the Ly, right, is you're going to have a node that's at the L equals 1/2 point, right? So this is the Ly 1/2, Lx 1/2, right? So essentially you're cutting this whole thing in half. And I realized I should have drawn like that, right? And so what's, if pictorially we're looking at it, you can, in a way, draw it out and be like, okay, right, like this is all going to then be, positive phase, right? This is, positive and negative, right? This is going to then be negative phased, right? And then this is positive in this case, and this is negative, right? In terms of like what the phasing is, right? And so that's the best that I can do for drawing out, what the landscape of a 2D particle in a box looks like, right, is like kind of doing like a topographical map. But you don't have to do all of that, right? What you can do is you can just simply think about each direction on its own, right? So if we're going from 0 to L over 2, right, and we're at the n equals 2 level, right, we're at this point right here, this is 50% of the full thing, right? Because the full wave is 100%. And so if we're at the L equals, when L is equal to L over 2, right, we're cutting it directly in half. And so we're only going to have 50% of that contribution. Same thing here, right? We're cutting it in half at the L over 2 region, right? So that's 50%. So there's only 50% of the x-axis, 50% of the y-axis. We multiply those two together, right? What we get then is that this region is only 25% probability of finding the electron there, right? Because we're just simply multiplying the probabilities of finding it at this point along the x-axis and finding it at this point along the y-axis in those cases. And so that's why, right, this right here is going to be 25%, because it's just simply taking those two parts right there. For the next one, right, we're looking at Lxy is equal to 0 to Lxy equals 1 region, right, for n equals 1. It doesn't matter what the n value is, because we're going essentially the full distance of the box. It's going to be 100%. Right, there's no difference in this case, right, because it's going to be 100% in the x direction, right, because you're going the full length of the box, and then it's going to be the 100% for the y direction, because again you're going that full length of the box there as well. It doesn't matter if it's n equals 1 or if it's n equals 14. If you're doing the whole box, right, the probability of finding the electron there is going to be 100% in those cases. So the final one right here, right, Lxy L over 3 to Lxy L over 2 region when n is equal to 3. So if we draw this one out, right, again, right, Lx 0 Ly in these cases. So we have n over 3. So that's going to be then the one where we have, two nodes that exist, right? Because it's going to go dip, dip, right? So you're going to get this right here, right? So there's a node that occurs here. There's a node that occurs here, right? And so that, because in a particle in a box, right, we're looking at a very simple sine wave in these cases, right? It's going to, at each point, it's just simply going to, cut it up. So this occurs at, 2L, or sorry, this is L over 3, and this is then at 2L over 3, right? So 33%, 66%, right, of the length of the box, right? It's always going to be cut up perfectly, right? There's not, each region, like each node is going to have, on its own, the same amount of area, so to say, right? And so then for the Ly direction, this is also going to be a n equals 3, right? So it's also going to have 3 nodes, right? So you're going to have one here, right? So this is Lx over 3 Ly, right? So this then becomes Lx over 3, and then this is then Ly over 3 2Ly, right? In those cases, right? So those are the conditions. Now, looking at it, right, what we can first do is be like, okay, what we're trying to look at is from this region right here, the L over 3, right, to this one right here, which is L over 2, right? That's the exact half point. So we're trying to, pictorially distinguish essentially what's going on for this part, right? And then right here, what's going on for this part right here. So looking at it, right, we know then if, because we're cutting up, this right here is going to be 33%, right? This whole region right here is 33%. This whole region right here is 33%, right, of the y component. This right here is 33%. This right here is 33%. This right here is 33%, right? Each one of those different, plot points is going to be 33%. The next thing is, right, so if we know that this whole area right here is 33%, we're cutting that in half now, right? Because going from, 33% to 66%, right? The halfway point for that is, 50% in these cases. And so what this now gets cut up to being, right, is simply half of 33%, right? So that becomes 16.7%, right? Or if you were to do it, right, this is a third, this is a third, this is the third, right? A third gets cut up more to, 1/6 in these cases. I wonder if I made a mistake I think I made a mistake on the key. Wait a second. Oh no. I know what the problem is. For some reason, the change that I made for week 2 didn't carry over. Interesting. I don't know why that is. All right. Well, now I know why people voted on this, because the problem that's in the answer key is different than the problem that is in the packet that I released. Let me make sure that like I didn't mess up somewhere. Oh, this is frustrating. I apologize for that. Man, why didn't anybody say anything? On Piazza. Let me check what I had posted. If it matches, if like the packet that I posted matches the key. All right. Okay, so the key has that I posted on Piazza, but the packet I posted does not. Weird. I don't know how I didn't catch that or anybody else did. Well, if you're trying to figure out how to actually solve the problem that I'd given in the thing, right? That's how essentially you do it, is you just simply cut everything up in these cases, right? So this becomes but the 16 right, so oh man. Okay, right. So it's 1/6 right here, right? And then this region right here is then 1/6 as well. Right. So it's 1/6 times 1/6, which is then 1/36. Right. So the finding your, electron there is then 1/36 in this case. I think I may have also like had the wrong answer on the key that I posted, right? Because that one shouldn't be 1/6 there either, I think, for that region that I had given. I'll fix those later, but now I know why. Okay. Yeah, I'll post the correct. Did you think we will be asked to do L? So it's not out of the question that that'll happen on the exam. I don't have the exam from last year that related to all this here, but I know years in the past they've done those. And so again, right, like when thinking about it, it all is very similar to a 1D particle in a box, right? The only thing now is that you're just simply adding, you're just simply multiplying all those different components and factors to it. But in terms of like qualitatively, how do you assess it? It's pretty similar, where you just simply, plot what it looks like, right? Like if you're doing a particle, in a ring type of problem, right? If this is your ring, right, the n equals 0 level is going to sit directly on the ring. If you're going to have a scenario, right, where you have where you go higher levels, right, then you're gonna start having the wave function move off of the ring, where you get this, and then it has like this, right, and stuff like that, and everything, right. But in terms of like how you approach those problems, right, it's still the same approach that you would use for a 1D, right? Like that's all we're doing right here, is we're just using the same approach that we would use for a 1D particle in a box problem, where we qualitatively look at it. But what we're just simply doing is we're looking at it first off from the x direction, and figuring out, okay, well, what's the probability of finding it in this quadrant of the x-axis, and then then the next thing is to be like, okay, well, now let's look at the y-axis, right? Like what probability are we looking at right there as well. So that's the it's pretty much the same approach, right? So if we're saying what's the probability of finding an electron from here to here, you're just like, okay, right, that's a quarter of the circle, right? That should be 25% in those cases and everything. If we're talking about probability, and if we're talking about the energies of the systems, right, like you just do the same approach that you would do for getting the energy, for a 2D and a 3D, right? All you're doing is really just like stacking up, what it is for the x direction, the y direction. If you're going 3D, right, the z direction. If you're doing a ring, right, what you're then switching up is, instead of it being strictly in the x and the y directions, right, because you're going around in a ring, there's momentum that gets factored in, right? But that just simply, is a proxy for what the x direction essentially is in those cases, right? And what L is, right? Because L just simply changes to what the angle is, right? And then the momentum is then just simply, the proxy of what the x direction is for a circle. So does LXY mean a value on the x-axis? LXY means that it's the, the value on the L-axis and then the y-axis. Right. So this is just me shorthanding my way to being like, right, this is LX is equal to Ly is equal to 0. Right. That's just me shorthanding it for myself, right? That the x and the y direction are both of those things, because you're just ending up still right at this quadrant right here, right? If it's the L/2. Will we ever be asked to find probability for a 3D box? You might, but again, it's the same approach that you would do right here, right? All you have to do is just think about, okay, well, in the x direction, what's the probability, right? Because all I'm doing right here is I'm just being, when I'm going through this approach, let me not use red for color reasons. What's a good color? Blue. Right. All I'm doing in this case right here, right, is I'm saying, okay, what is the likelihood of finding the electron in that, right, that corridor of the x-axis, right? So that's the first thing that I'm doing. And then the next thing that I'm doing, right, is then looking at the y-axis, where I'm like, okay, well, what's the likelihood of finding the the probability of finding, the electron in that corridor of the y. And now I'm just simply taking those two things, multiplying them together, and that's how I end up, finding out what the probability of finding the x value is in that really small region of those two corridors in those cases. And so that's the same thing that you can then apply to, a 3D one, right? So if we were to go and do a 3D one for, problem 3, right? So we're already at 1/36. If, we assume then that the L, that the Z, the length of the Z, axis is then, that of that part of the box is the same then as the Lx and the Y, right? We're talking about a true cube then in that case. You can do the same approach, right? Where we're still looking at n is equal to 3, excuse me. Right. And so then we're just looking at that quarter. So again, it's only going to be, 1/6 of the time you're going to find it in that corridor. And so then you just take 1/36 and you multiply that, by 1/6, and you get, what is it? 1/36 times 1/6. Not in, where's math? Right, 1/216, right? The probability of finding, right, in a 3D particle in a box in that specific cube region, right, is 1/216, right? So 0.004, right? So, less than a percentage point. But again, right, it's the same basic approach, right, that we can do with a 1D. We can apply that to the 2D and the 3D most easily, because, right, all we're just simply doing is just adding different axes in those cases. And so we can do that. When you start getting to like a sphere, it can become a bit trickier if you're looking at different X, Y, and Z directions, and that's completely out of the scope, because I think for that one you'd really have to, I don't know how you could really easily pictorially identify what's going on. But you could do right for that one. I mean, calculus I think would probably be the easiest, like probably taking a whole semester of calculus and then figuring out how to like integrate sphere coordinates and stuff like that would probably be easier than trying to draw it out and then figure it out. But for a 3D, right, it's just it's the same approach, right? And same thing with one, right? I mean, that's all it is, just simply taking what we know and how we approach a 1D particle in a box, and then just saying like, okay, right, we're in 1 dimension. Okay, we can do this now in 2 dimensions, because all we have to do is just do it twice and then just multiply those results in those cases. So that's how for the probability part. Cool. All right. Well, let's see if there's a difference. Let me see. I think this is the same, right? 1.5 angstroms. Let me check the answer key. 1.5 angstroms. Okay. So B shouldn't be a problem.